Welcome back to this course on ILP, DLP and TLP. The topic of this lesson is dependencies and hazards. As explained in the previous lesson, we want to schedule instructions dynamically in hardware and potentially execute them out of order. To be able to do so, we need to determine if instructions depend on each other. This lesson explains the different types of dependencies. There are three different types of dependencies. The first one is data dependence, also called true data dependence. Two instructions are data dependent if there is flow of data between them. They cannot be reordered but need to execute in order. The second type of dependencies are name dependencies. In this case, there is no flow of data, but there is a dependence because the instructions use the same name, for example, the same register. As we will see, such dependencies can be eliminated by a technique called register renaming. In fact, there are two kinds of name dependencies: anti-dependencies and output dependencies. I will show an example of both in a few slides to come. Finally, there are control dependencies. An instruction is control dependent on a branch if the branch determines if the instruction is executed. As I will show later, we might be willing to violate control dependencies provided this violation does not change the outcome of the program. Let me now precisely define what a data dependence is. An instruction K is data dependent on an earlier instruction I, earlier in program order, if I produces a result used by instruction K, or if K is data dependent on another instruction J and J is data dependent on I. Consider, for example, this example. Load to F0, add double F4, F0, F2 and then store F4. In this example, the add double is data dependent on the load double, since the load loads F0, which is used by the add double. Similarly, the store is data dependent on the add double, since the add double produces F4 and the store stores F4. By the second rule, the store is also data dependent on the load, since the store is data dependent on the add double, which in turn is data dependent on the load. A data dependence may result in a read after write hazard, but it doesn't have to. According to the textbook, dependencies are program properties, whereas hazards are properties of the microarchitecture, the organization of the processor. According to Hennessy and Patterson, a dependence results in a hazard if a stall cycle is needed as a result of the dependence and the organization of the processor. If no stall cycle is needed, the dependence does not result in a hazard. If we assume this code is executed on the pipeline processor with multi-cycle operations that I presented in the previous course, the data dependencies will result in a raw hazard. The add double will stall in its decode stage because of the load use data hazard, and the store will stall in its execute stage because the add double requires 4 execution stages. Now I turn to name dependencies, anti-dependencies and output dependencies. First, I explain anti-dependencies. There is an anti-dependence between an instruction I and a later instruction J, again later in program order, if instruction I reads a variable that is written by J. So it is exactly the opposite of a data dependence. An anti-dependence may result in a write after read hazard, war hazard, depending on the microarchitecture of the processor. Here's an example. B is assigned the value 3, A is set to B plus 1, and finally B is set to 7. In this example, there is an anti-dependence between the second instruction, instruction I, and the third instruction, instruction J, because I reads B and J writes B. In principle, with the emphasis on in principle, we cannot execute J before I, because if we do so, we would use the wrong value, namely 7, instead of the correct value 3. Such dependencies are called name dependencies because the instructions use the same name, which can be a register or a memory location, but there is no flow of data between them. In fact, such dependencies can be eliminated by renaming the variable. Here's a renaming example. In this example, the destination variable of instruction J has been renamed to B1 as highlighted in red. Now instruction J can be executed before instruction I. Of course, all later occurrences of the variable B1 also need to be renamed to B1. The second type of name dependencies are output dependencies. A later instruction J is output dependent on an earlier instruction I if I and J write the same variable. An output dependence may result in a write after write hazard. Here's the same example as before. B is set to 3, A is set to B plus 1, B is set to 7. In this example, there is an output dependence between the first and the last statements, since both write the variable B. An output dependence is also a name dependence and can also be eliminated by renaming, as shown in this example. In this example, the first two occurrences of the variable B have been renamed to B1. Now statement J can be executed before or in parallel with statements I and K. Finally, I remark that the read after read case is no dependence or hazard. Reading a variable can be performed in parallel or out of order. As said before, according to Hennessy and Patterson, dependencies are program properties, whereas hazards are properties of the microarchitecture of the processor. A hazard occurs only if the dependence results in a stall cycle. Let's consider an example to make this clear. Here's the example: an add immediate that writes to R1 followed by a branch that uses R1. No matter what, there is a data dependence between these two instructions, as indicated by the blue arrow. This data dependence results in a raw hazard if the branch is executed in the decode stage, as we assumed in the canonical 5-stage pipeline. This pipeline diagram illustrates what happens if the branch is executed in the decode stage. A stall cycle is needed because the value of R1 is not available until the end of the execute stage of the add immediate. On the other hand, if branches are executed in the execute stage and the processor performs forwarding, no stall cycle is required. In this case, no stall cycle is needed and no raw hazard occurs, as this pipeline diagram illustrates. In this case, the result of the add immediate can be forwarded to the branch and no stall cycle is needed. Finally, I remark that other researchers are less strict about the difference between dependencies and hazards. So you might read scientific papers where the authors write that there is a raw hazard between two instructions, whereas Hennessy and Patterson would say there is no hazard but a data dependence. The third type of dependence is control dependence. A precise definition of control dependence is not easy, but informally, a statement S is control dependent on a predicate if the predicate determines if the statement is executed or not. Here's an example. If P1, then S1, else S2. If P2, then S3. In this example, statements S1 and S2 are control dependent on P1, and statement S3 is control dependent on P2, but not on P1. In principle, again with the emphasis on in principle, a control dependent instruction cannot be moved before the branch, since then it would be always executed instead of being controlled by the branch. Similarly, an instruction that is not control dependent on a branch cannot be made control dependent on that branch, since then it would only be executed if the branch condition is fulfilled. I said in principle, however, because there are several situations where we can violate control dependencies. On this slide, I illustrate when instructions may be scheduled across or over branches, thereby violating control dependencies. An instruction that is control dependent on a branch may be executed before the branch if its result is used in only one branch path. Here's an example. If P then T is set to 5 and A is set to T times B. Now assume that the variable T is not used in the rest of the function, which I try to emphasize by declaring T inside the then part of the if statement. Then this program is equivalent to this program where T is set to 5 before the if statement, so it is no longer control dependent on the predicate P. Similarly, a statement or instruction that is not control dependent on a branch can be made control dependent on the branch if its result is used only in the branch path where it is moved. That corresponds to the reverse of this example. The example on the previous slide shows that control dependencies are not critical program properties that must be preserved and therefore are not fundamental performance limits. We may violate them provided the correctness of the program is not affected. In other words, we may execute instructions that do not have to be executed, provided they do not do something that is irrevocable. This is the fundamental idea behind speculative execution, where instructions are executed before knowing if they should be executed. Properties critical to the correctness of a program that must be preserved are data flow and exception behavior. If an instruction I is data dependent on instruction J, meaning data flows between them, then they must be executed in order. Why exception behavior needs to be preserved, I explain on the next slide. Instruction reordering or dynamic scheduling must preserve exception behavior. This means that the instruction reordering may not cause an exception that would not have occurred if the instructions would have been executed in normal program order. An example to make this clear. If P is not the null pointer, we dereference P and then we set Q to the dereference value square. This C code can be translated to this MIPS assembly code. First we test if register R1 containing the pointer P is 0. In C the null pointer is indeed null, 0. If R1 equals 0, we branch to the end if label, thereby skipping the then part of the if statement. Otherwise we load the value pointed to by R1 into F0 and then we multiply F0 with itself. There's a load use data hazard between the load and the multiply as indicated by the blue arrow. Therefore, we want to execute the load as soon as possible. So we schedule the load before the branch as shown here, where the load is highlighted in red. Since the result of the load is used only in the not taken path of the branch, this might seem like a legal transformation. Unfortunately, this transformation may cause a memory protection violation exception that should not have occurred. If R1 equals 0 and therefore P is the null pointer, the load will attempt to read from address 0, which is illegal because address 0 is reserved for the operating system. So this transformation is not legal in this case because this exception would not have occurred in normal program order. To deal with such cases while still being able to schedule loads before branches, modern high-performance processors support constructs that ignore the exception if the branch is taken and should not have been executed. How this works, I will explain in a later lesson. Finally, an exercise to test yourself. Indicate the dependencies in this MIPS assembly code and also indicate the type of dependence. To keep things simple, you only have to indicate the dependencies within a single loop iteration and not the dependencies across loop iterations. This completes this lesson. Thank you for watching. In the next lesson I will describe Tomasulo's algorithm, which is the basic dynamic scheduling algorithm allowing out-of-order execution. Hope to see you back.